right. හැමෝටම සුබ දවසක්. අපි discussion එක පටන් ගමු පුතා. Revision tube number 3 from question number 269, right? Number 269. At what speed is a car approaching a stationary observer if he hears the sound of the car horn with the frequency 10% higher than the actual frequency, right? If this one is the source, travel with the velocity of v us approaching the stationary observer. Stationary observer, v naught is 0. Sound is going towards this side with the speed of sound in air v. Frequency emitted by the source is f naught. Apparent frequency is f. Then apparent frequency is written wave velocity relative to the observer, just v. Wave velocity relative to the source, both are traveling into same direction, right? So minus us into f naught, right? Okay. Then you are given 10% more than, then you can say this is 100f. This one should be 110f, like this. Here. This one is this one. Emitted frequency, if it is 100f or 100, no matter, just 100, then this one is 110, right? Then it's 110f equal v 340 divided by v 340 minus us into f naught 100f, right? ff cancel. 10 cancel. This becomes 1.1. No, 11 by 10. No? It's 1.1. 340 minus us equal 340, right? Then 340 into 1.1. This one taken into the other side, 340. Here goes to the other side, 1.1 us, right? 1.1 us. Then here we have 340. 1.1 minus 1 equal 1.1 us. Then you can have the final answer. The answer should be 1.1 us equal 340 into 0.1. No? Then velocity becomes 30.9 ms minus 1, like this. That could be the answer, no? Yes. Okay. Question number 270. A train approaching a hill at a speed of 40 km per sound, 40 km per hour, sound the whistle of frequency 580 hertz. The train, frequency 580 hertz, with the velocity 40 km per hour, emitting the sound towards the hill. No? When it is at the distance of 1 kilometer from the hill, the horning is made. This is 1 kilometer. A wind with the speed of 40 km per hour is blowing in the direction of motion of the train. A wind is blowing with the velocity 40 km per hour. 40 kilometer per hour. Roman 1, frequency of the vessel as heard by the observer on the hill. Let it F1 to be found. Next, distance from the hill at which the echo from the hill is heard by the driver, and the frequency and its frequency, echoing. Then this is the emitted frequency. That one is the emitted frequency. Then it turns back, no? When it is turned back, the train may be lied at here. Distance at which the hill at which the echo from the hill is heard by the driver. Distance from the hill. They need this one. Let it X. Right. You asked to find X and frequency heard by this one, no? Okay. Speed of sound mentioned 1200 kilometer per hour, right? Then effective speed of sound towards this side, towards right side, effective sound speed. Towards this side, effective sound speed, both are into same direction, supportive one, 1240 kilometer per hour. Here sound speed. Sound speed towards the hill, right? Then here sound speed towards backward, right? Returning one, returning wave opposed to the direction of wind, it should be 1160 kilometer per hour. This is the new sound speed, right, Buddha? Okay, then they need first one, frequency heard, F1. So we can say F1 equal observe at rest, wave velocity, this one, towards this direction, US into F0. Same as that question, right? F1 to be found, V 1240 over 1240 minus 40, no? Into F0. F0 is the emitted frequency, 580. Then F1 becomes 1240 divided by 1200 into 580. Can we take the final answer? It's 599.33 hertz or nearly 600 hertz, right? Frequency has increased. Right. Okay, next one. That's Roman 2. Distance. Finding X, no? We should find X. Then let the time taken to travel the train from here to here. Let the time taken to travel the train from here to here, T. Then time taken to travel the sound from here to here, T1, from here to here, T2. Sounds travel from here to here, T1, here to here, T2. Two velocities. Then you can say T equal T1 plus T2, right? T equal T1 plus T2. T equal T1 plus T2. Then T, we can say from here to here, we can call that S equal ut. For the train, S here to here, 1 minus x, velocity 40 time t. Then t becomes 1 minus x. Here, 1 minus x divided by 1 minus x divided by 40 equal t1 from here to here for this sound. We can apply for the sound distance traveled by wave S equal ut again. S is 1 kilometer, velocity of the sound 1240 into t1. So we have here 1 over 1240 plus t2, time taken from here to here. It goes with the velocity of 1160. No? Then for this returning one, we can write here S is again ut, S is x equal velocity 1160 t2. So here t2 becomes x divided by 1160. Done. Okay, Buddha. Can we manage the calculation? 0 cancel. 4 times here 1, 1 minus 6 equal here. 4 times here 3, here 31 plus this one is x over 116, no? It's 29. Then we can take this one into the other side, 1 minus x over 29 and equal 1 by 30. It's better to take this one into the other side. Take this one into this side. It's 1 minus 1 over 31 equate x plus x over 29. So we have here 31 of 31 minus 1 over 31. Here 29x over 29 plus x over 29. So here 30 of 31 equal 30x over 29, right? Then x becomes 29 over 31 kilometers. Okay. Can I have the answer? Right. Let's take question number 271. This one roughly 0.937 kilometers, no? Okay, right, done. Next one, 271, right. Read the question carefully. (271). A whistle emitting a sound of frequency 440. Whistle emitting the sound 440 hertz is tied to a string 1.5 length and rotates with the angular speed of 20 radian per second, like this. This is revolving a circular motion. String of length 1.5 meters, clear. Rotates with the angular velocity 20 radian per second. In the horizontal plane. Calculate the range of frequencies heard by the observer stationary at a large distance from the vessel, right here, like this position, the range of frequency, right? Then at a certain position like this, at a certain position like this, right? This person hears the sound directly while coming towards the observer like that, no? While incoming towards the observer right here. And if the source goes right here into this side, the sound is ejected from the source, which is similar to the source moving away from the stationary observer. So this is incoming one, this is outgoing one, towards and away, towards and away, right? To the, and here to it's F equal V over V minus US into F naught, and here away, no, with the same velocity, F2 is V over V plus US into F naught. Can you manage the calculation quick as possible? Let's start now. Take the speed of sound in air 340. It won't be, it is not mentioned in here, no? Right. Take 240 sound speed. V naught is 240 meters per second. And from this one, velocity becomes V R 1.5 into 20. V equal, it's 30 ms minus 1. Okay. It's a sound speed in air 330, right? Not 240, it's 330, right? Okay. Then here, F1 is V 330 divided by V minus US 330 minus 30 into 440. And here we have 330 over 330 plus 30 into 440. Right. අතින් සුළු කරන්න කැල් පාවිච්චි කරන්න එපා. This one, final answer 484 hertz. And this one, $392 here. Done. Right. Let's take the other one. Question number 272. We can draw the variation of frequency heard. Can we copy this one too? Apparent frequency heard by the observer with the position of A to B. It's A to B, like A here, B here. When the source right here, right? When the source right here, velocity directed towards this side, transmit of wave, this one wave, this is the wave, right? Wave motion is this one, this broken line is the direction of wave motion. Wave motion into this side, velocity of the source perpendicular to that direction, right? Therefore, at here, apparent frequency is same as real frequency of the observer. Then here, coming towards now, it will be varied like this, right here. Okay, at this point, at the exact midpoint of the drawn path from here to here, like C, apparent frequency same as real frequency. Done. Can we copy this one too and start the question number 272? Right, next one. Question number 272. A whistle of frequency 256 is moving towards the stationary listener. 272. Hertz is moving towards the stationary observer. Stationary observer. US0. With the speed of 120th. Sound speed, if it is v, this velocity is v by 20. While heard the listener before and after the locomotive pass him. First, coming towards v over v minus us into f naught. F equal v over v minus us v by 20 256 hertz. And far away, when this source passes the observer, frequencies v over v plus v by 20 into 256. They need the separate values now. Now, can we simplify this one? Yes. F1 is here, v cancel. It's 1 by 20. 1 minus 20 minus 1 into 256. Then F1 becomes 256 into 20 of 90. And here we cancel 1 by 20. 20 plus 1 into 256. Then F is 20 into 256 divided by 21. F. Okay. Take the final answer. This is 252.4 hertz. F2. F1 is 269.5 hertz. Right. 273 clear. Next, 272 done. 273. Right. Can we complete it now? A motor car moves in the shown direction with the speed of 5 ms minus 1 while standing the horn frequency f0. Horn frequencies f0. An observer A and B remain stationary behind and front of the car as shown in the figure. A diagram is mentioned. Right, here we have car. These 2 points are having the observers A and B. This guy A, this one B. Vehicle travels towards this side, no? Okay. Then the car is shown in the figure, while another observer C moves with the uniform velocity with the speed of 5 ms minus 1. This one is C, moves with the velocity of 5 ms minus 1. Clear. This one stationary, US V0 is 0. V0 is 0. The car moves with the direction 5 ms minus 1. Right, done. Next. In front of the car, if the frequencies of the horn heard by them are FA, this one heard frequency FA, frequency of FC is this one, emitted frequency is F. So they exactly FA less than F now. FA less than F. Reason, source travel away from the stationary source of A. Relative to this and this, there is no change of speed. There is no relative motion of these two, as both are traveling into same direction here. This one emitting the sound towards right side, traveling towards right side, velocity of the source also to right side. Then there is no relative motion of this and this. Then FC should be equal to F. F means F0, right? Emitted frequency F0. So then this one, B stationary one, no? Here we have B. This is also at rest. Then this is the highest frequency of Earth, no? FB greater than F0, reason, source coming towards the observer. So the correct answer is FA is the least one. Next one, highest one is FB, right? FB larger one. FC equal to F0 and largest one is FB. Right, can we manage third answer? Possible answer is third one, then it should be FB, right? Okay, third answer is the correct answer. Okay. 274. In the above question, if the vehicle was at rest while sounding the horn in the same frequency, sounding the horn with the same frequency, okay, A and B was moving towards the vehicle 5 ms minus 1 with the uniform speed. This one travel with 5 ms minus 1 for the second question, right? 274. This one goes with the velocity of 5 ms minus 1. 5 ms minus 1, 5 ms minus 1. Source and the observer same velocity, then FA equal to F0, right? And this one goes towards this side, towards the observer by 5 ms minus 1, then FB should be greatest one, then F0 and the other stops, right? Okay. Then the new relationship between them. Then FA equals FB, clear? Sorry. FA equals the combination. FB is the largest one. Going towards, no? B slide in front of the car, then B goes towards the vehicle, no? Yes. The uniform speed, and C is moving as above. A and B moving towards the vehicle. Towards the vehicle. This one goes towards the vehicle, then FA is F0. Done, this one correct. And this should be the arrangement, no? Right, then FC same as F0, right? F0, like this. Right, now select the correct answer. This is same as FC, no? FC is equal to FA equal to F0, largest one is FB, right? Write down the answer. FC equals FA equals real frequency. Largest one is FB. Right. What is the correct answer? Right. Can we check? Question number 275. 275. Due to a certain siren made by a sound source with the wavelength of sound propagating through air, forward was lambda naught. Lambda naught, no? Due to the certain sound, sirens emitting the sound into a certain direction, the sound source of wavelength propagating through air, forward was lambda. This wavelength is lambda, right? Okay. When the speed of sound through air is v, this is v, the sound moves towards the stationary observer with the speed of vs. Take this one vs, stationary observer. Okay, done. Right. Next, if the wavelength of the sound propagating is lambda naught, then they need the combination, no? Yes, then if the wavelength of the sound propagating, read it again, when the speed of sound through air is v, the source moves towards the stationary observer with the velocity of us. Initially, you are given a siren made a sound source, the wavelength of the sound propagating through air forward was lambda. Initial one is when we apply v equal f lambda, v speed of sound, f frequency f naught, lambda is lambda. This is first one, right? Okay, and you are given if the source moves towards the stationary observer while moving towards this side with this one, then lambda becomes, yes, Sudha. Then if the wavelength of the sound propagating is lambda naught, this one is lambda naught, then wave velocity changes, no? Wave velocity becomes v minus vs. V minus vs. Then for the propagating wave, we can say v minus vs into emitted frequency f naught, lambda should be lambda naught, right? Second one. Then we can divide these two. Can we divide second and first? 2 divided by first, 2. V minus Vs divided by V equal F naught lambda naught over F naught lambda. F naught cancel, then lambda becomes subject in lambda. Lambda is lambda naught. We have subject lambda times of Here we have V over V minus Vs over V, right? V cancel, then lambda naught equal lambda times of 1 minus Vs over V. This could be the calculating answer. Lambda combination of lambda and lambda naught, right, Buddha? Right. Third answer is the correct answer. This pattern is not in the past paper question, right? Comparison of lambda, we have only one MCQ question, that is 2013, like that. It is the only question related with the wavelength. May process first emitting the value of V equal F lambda by subjecting the stationary source. While this is stationary, we have to apply this equation. Secondary, while it is moving with the relative velocity, we have to apply the equation for the source, right? Not for the observer. These two configurations allowed only for observer. Sorry, only for source, not for the observer. Then after that, we can take the combination with each other. That variation is the variation of apparent frequency of the observer, right? Okay. Next one, 277. Read the question. When a car out of the tunnel with the speed of 10 ms minus 1, a car travel with 10 ms minus 1, the sound of the horn frequency 350 ms minus 1, find the beat frequency of the driver in the car due to the sound wave that reflect back after hitting the tunnel wall. Like this one is the wall. The emitted sound is this one. Apparent frequency is F1. Reflected sound is this one. Apparent frequency is F2. This is the emitted frequency, 250 hertz. No? Let this one F0. Beat frequency, let it delta F equal F2 minus 350. No? If you can remember, beat frequency is 2 F0 V0 divided 2 F0 US divided by V minus US as the source traveling towards the sound barrier, right? Or if becomes delta F equal beat frequency equal to F0 US over V plus US if the source travel away from the obstruction, coming towards and coming away, right? If you can memorize this one today, that will be easy for MCQ question. But essay question, you have to derive, right? You have to derive, first of all, you have to write the equation for the emitted wave by considering this one source and this one as the observer. And for the reflected wave, this one becomes source and this one becomes observer. This one source, this one observer, and observing frequency of the driver in the car, F2 and F0 heard together by subjecting the beat frequency. Right, that should be the procedure. Then it's better to use this one, right? Okay, then delta F equal, okay, 2 F0, F0 350, speed of sound, speed of source 10 divided by speed of sound 340 minus 10. This could be the simplification. Then 277 answer. Can we manage the answer? It's 2 into 350 into 10 divided by 330, right? Okay. 1 0 cancel. Here. 700 divided by 33. Roughly, what would be the answer? It's like 21.21. Closest answer is third one, no? Okay, write the value here, 21 hertz. Nearest value is 20. Okay. And we missed 276, no? Okay, can we take 276 too? 276. Okay, a train is moving with the speed of 20 ms minus 1. This is clear, no? Right. To 76. A train travel with the velocity of 20 ms minus 1. It's a train here, 20 ms minus 1. When the train moves past the passenger by emitting the horn of frequency, a certain frequency, the change of apparent frequency was 34 hertz. If the speed of sound through the air is 340, the frequency of the horn heard by the train is frequency of the horn sounded by the train. If this one is the observer, right? While this one is coming towards, apparent frequency is F1. And when it passes the passenger, and frequency apparent one is F2. Then when they come into it, F equal V over V minus US into F naught. And going past, F2 equals V over V plus US into F naught. And you are given, in the question you are given, the difference is 34, no? Change of frequencies, difference of those two frequencies, this and this. Then you can say F1 minus F2, which means V over V minus US into F naught minus V over V plus US into F naught. This difference is equal to 34 hertz. That would be F naught common factor and V common factor. Here we have V minus US, V plus US. No? V minus US and V plus US common factor, common denominator. Here V plus US minus V minus US within bracket. Done. This could be the simplification. One, it's 34 equal. Frequency heard unknown, 240. Sound speed is 340. Bracket here, minus minus plus 2 US. 2 US, US is 20. And V minus V cancel. Today here becomes V minus US, V plus US, V squared minus U squared, no? 340 squared minus velocity 20, 20 squared, done. This could be the substitution. Then frequency, simplify this one. F naught becomes 280. Pick the correct answer. Right, 278. A sound source is performing the simple harmonic motion. Sound source performing the simple harmonic motion here and there. No? Sound source performing the simple harmonic motion. Right, at here, maximum velocity. Here, velocity is 0. Here, velocity is 0. And stationary observer lied out of the location right here. Stationary observer, then you are asked to identify frequency heard by the observer. No? Frequency heard by the observer, F. PQ are 2 points in between OA and OB respectively. Then the variation of the apparent frequency F heard by the observer during the time when the displacement of S is from P to Q. P to Q is this one, here to here, no? P to Q. P to Q. During the time when the displacement of S is from P to Q through O is correctly given by. For the P to Q, this velocity won't be zero, right? At here, the real frequency same as apparent frequency, F naught, F naught. But today you are asked to draw the variation from here to here. Then it won't be zero velocity, no? Then frequency of F naught is not allowed at here and here. Then if the F naught frequency is right here, and then let's see, when this source travel from here to here, first thing travel from here to here. At here, right, this one is source traveling towards the stationary observer. You are asked to draw the variation from P to Q, right? P to Q. This point is P, this point is Q, right? P, starting from here. It goes away. Source goes away while increasing the velocity. Then apparent frequency is moving away like this, no? V plus US into F naught. Then velocity in the simple harmonic motion is not uniformly varied. Velocity of simple harmonic motion is not uniformly varied. Therefore, velocity changes. Velocity exactly changing, right? From here to here. Then denominator change. Then apparent frequency, this one, less than this one, right? But from here to here, velocity increases as the denominator is increased, frequency gradually decrease. And at here, right, frequency heard by observer becomes the least value, right? And from here to here, frequency again, from here to here, velocity decreases, and from here to here, velocity increases. Velocity from here to here decreases. Velocity decreases. Then downward decreasing velocity now going to increase, right? From here to here, frequency decreases. And from here to here, frequency increases, but smaller than real frequency. Smaller than real frequency. Then frequency decreases right here and then increases like this. First answer should be the perfect answer. Clear with the write down. Can we manage it? From here to here, no? Okay. 279. The person gently released the tuning fork vibrating with the frequency F naught from the top of the building. This one is the tuning fork of the frequency of naught is dropped from the building. Okay. Then the variation of lambda against time they need, no? Okay. The apparent wavelength is lambda naught of the sound propagating during the tuning fork heard by the person from the time t when it was dropped is correctly given by. This is the observer at here. Velocity V naught is 0, no? Right. Here we have, this is going down, source is going down. with the increasing velocity under gravity, then sound is moving towards the observer. Sound is moving towards the observer, but source is traveling back. No? Source is going away. Source is going away from the stationary observer. So we can manage like this. How? Let's see. This is going down. It's F equal V over V plus US into F naught. Right. Then they need the apparent frequency, apparent wavelength of lambda naught. No, the variation of apparent wavelength from this one, we can say here F naught is V equal F lambda. Then lambda becomes V over F, right? Okay. F equals V over lambda. Assuming this one at rest, it is this one. Frequency is written. Sound speed over lambda. Lambda is the exact one, right? This is a constant value emitted from the source and equals V over V plus US, this one, in F naught. F naught is the frequency. We can manage it, no? From the given one. This is the real frequency, no? This one should be taken to here. Real speed of sound from here. Lambda is the emitted frequency. This is real one. This one is the apparent frequency, no? Right. They need the variation of apparent wavelength. This one is the frequency, no? Or we can use just V equal F lambda right here. Wave velocity relative to the observer at rest. Source is moving, both are moving towards same direction. V plus US equal F naught real frequency, then wavelength. Then relative wavelength changes like this, no? So this one is the variation. Then lambda varies with the time, no? Today we all know V equal U plus AT. Velocity of the source obtained is AT, no? A is G, gravitational acceleration. Then velocities uniformly change. Let's see. Velocities uniformly change. We can take this one with this one. So it's V plus GT equal, from this one or this one, we can take the final answer. Lambda naught, right? It's lambda, apparent wavelength. Then lambda becomes V over F naught plus GT over F naught, no? Then lambda becomes G over F naught into T plus V over F naught, right? Done. Then it seems Y equal MX plus C, no? It seems Y equal, from this one we can take that value as well, just using V equal F lambda for the emitted wave with the speed of relative wave velocities V plus US, right? F naught is the ejected frequency by the source. Lambda is the apparent wavelength. If this is apparent wave speed, then this one is rearranged by using this one. Then T is in x-axis, G constant, F naught constant, gradient constant. It won't be the curved one. V constant, F naught constant. It seems intercept, no? Then graph possible one is this one. Okay, then what is the correct answer? Correct answer is first answer, right? Okay, 280. Let's take 280. A motor car moves with the speed of 10 ms minus 1, while the speed of the wind is 5 ms minus 1, blows the same direction of the movement of the car. Car is this one. It goes with the velocity of 10 ms minus 1 towards the same direction. Wind flows with the velocity of 5 ms minus 1. And the speed of sound through air is 335 ms minus 1. If speed of sound in air, then Pute, you have to say 335 plus 5 is the effective sound speed, 340 ms minus 1. Okay, right. Next. A stationary observer in front of the vehicle a certain distance away, when the vehicle sounds the horn of frequency 1000 hertz. When the vehicle sounds the frequency 1000 hertz. Right. The apparent frequency heard by the observer is apparent frequencies. It's a stationary observer is in front of the vehicle here, no? This is observer. Then its V becomes V minus US into F naught, right? Okay, then F is V 340 divided by V 340 minus US 10 into F naught 1000. So take the final answer. Here we have 34 into 1000 divided by 330. It's 33, no? 0, 0 cancel, 33. Correct answer is fourth one. Okay. 281. Read the question. A vehicle moves when a motor car moves towards the stationary motor with the velocity 5 ms minus 1 while sounding the horn of a certain frequency. Okay. The variation of apparent frequency of the driver F dash with the time correctly represented by. Towards the stationary observer there. From the stationary observer, apparent frequency vary with the time. Apparent frequency variation against time t. Initially coming towards high frequency offered, but just passes, frequency drop down. Can we rearrange the final answer? Can we rearrange fourth answer? Fourth and third and fifth answers all are correct. But can we manage it? It's not, it won't be the slanted one, right? Direct one, right? Okay. That is the variation of speed of sound in air, no? Yes. Okay. Can we manage next part? Revision number 3, part C, optics, I and defective I. Okay. I and defective I. Okay. Define the least distance of distinct vision. But a distinct vision is the clear appearance, no? Distinct vision, like this. If you have this kind of, eye position, when you keep the eye in front of the object of 25 centimeter, it will form the image on the retina clearly, right? Like this is called the clear appearance of the shortest object, shortest distance. And when you keep the object at infinity, like this, object is at infinity, they are forming the image on the retina by changing the curvature of the eye lens. This is called far point of the distinct vision. This is far point of the distinct vision. This is called near point of the distinct vision. Near point of the distinct vision. Here, infinity. Then, clear observation zone of the eye is distinct vision. Then, near point of the distinct vision, the closest distance that can be kept an object to see the final image with long time with minimum eye pain. Then we can define this one, the shortest distance that the person can be seen. Okay, write down. Can we copy this one to that on the given space, or anywhere can we copy this one first? Okay, then write down the shortest distance shortest distance that the object can be kept in front of the eye to see the clear image, to see the clear image, to see the clear image, to see the clear image by the normal eye. Normal eye. Next, 284. Explain what is short-sightedness by drawing the normal eye, defective eye, and corrected eye. Okay, let's see. Right. In the normal eye, it short-sighted one. Here we have the eye. Eyes directed to far object. Principal axis. Far object. Emitting the light rays parallel to each other. Then this is the clear formation of the image for the far object. This is called normal light, right? This is normal light. When it is defected eye, the infinity light rays, which means the parallel light rays, will be converged in front of the eye. Reason, this person has the defective eyeball like this. This could be the real eyeball. This is real eyeball, broken one, right? This should be the real eyeball, but this person has slightly larger eyeball. This is defective eyeball. This one is real eyeball. Defective eyeball and real eyeball. They are converging right here. Perfect. This is the defective eye. Then we should identify defective eye slightly larger than diameter, slightly larger than the real eyeball, right? Okay. Next session, But today, this person can see, a certain distance in front of the eye. Light rays emitted from a certain point will be converged right here. Will be converged right here to form the image on the retina. This is called far point of this defective eye. Far point of defective eye is this one, right? Okay. This point can be clearly seen, but infinity won't be seen. Here we have blurred image. The image formed on the retina is blurred one, right? Okay. In the correction, we are using a diverging lens. We need to diverge these two light rays until focusing on the retina. So we have to use diverging lens, concave lens. Or refractive index of the medium in front of the eye. In front of the eye, refractive index of the medium, we can increase, no? If the refractive index of in front of the eye is increased, then ability of converging the light ray, we can reduce, no? Ability of converging, we can reduce. If you can reduce the ability of converging process, these two light rays will be formed, will be converged on the retina, right, Buddha? If you can increase the refractive index, by increasing refractive index in front of the eye, we can make the corrective eye. Then when you are swimming, if you have this kind of error, when you are swimming underwater, this error may be corrected. But corresponding refractive index in front of the eye should be manageable one for the refracted light rays until reach to the retina. But without changing the refractive index in front of the eye, we can use concave lens. How? Then, after placing the concave lens, a parallel beam of light now fallen on the lens, then they are diverging from a point, on the principal axis. This is constructive one, broken line. Then we have to select the focal length of this, right, until these two light rays are diverging from a point on the far point of the defective eye. This could be far point of the defective eye. Then this serves as the object to the eye lens. Then will form the image on the retina, same as this. When you keep the eye at here, when you keep the object at here, no doubt, image will be formed on the retina. But when you keep the object after wearing the lens at infinity, with a parallel beam of light coming from the infinity object will be formed the image at the point of far point of the defective eye. It serves as the object to the wearing lens to form the image on the retina. Is that clear with that? Done. This is the corrective eye. Then you can consider objective distance as infinity. This one as image distance for the wearing lens, and focal length is this one. By using the lens formula, you can find the combination of U, F, and V. Anyhow, as U is infinity, then the focal length should be equal to V. Then always short-sighted defect is corrected by varying the focal length, which is equal to the far point of the defect in y. Right. Take few minutes to complete these three diagrams. Let's start. Right. Can we see next one for that? 285. 285. 285. 284, you are asked to explain, no? Can we write at the given space for that? If you have enough space, write down. In the short sightedness, infinity objects are not clearly seen. Infinity objects are not clearly seen by the defective eye. By the defective eye. By the defective eye. By the defective eye. Next point. But at the selected far point of the defective eye, at the selected far point of the defective eye, at the selected far point of the defective eye, is clearly forming the image on the retina. Clearly forming the image on the retina. Next point. Then the eyeball of the defective eye, 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 slightly larger than the real diameter of the eyeball. Slightly larger than the real diameter of the eyeball. Real diameter of the eyeball. Done. Right. Next. Okay. Next point. After wearing the concave lens, after wearing the concave lens, after wearing the concave lens, it will form the infinity, it will form the image. It will form the image. It will form the image at the far point of the defective eye, at the far point of the defective eye, and it serves as, and it serves as, and it serves as, and it serves as the object, and it serves as the object, serves as the object to the eye lens, serves as the object to the eye lens to form the image on the retina, form the image on the retina. Done? Right. Clear. Right. Next one. Explain what is lone sightedness by drawing the normal eye, defective eye, and corrected eye. Right. In the long sightedness, you can see long distance object, no doubt about long distance objects. But the doubt is close distance one, no? Doubt is close distance one, especially when you keep the eye at the least distance of distinct vision of the object, right? It will form the image on the retina right here. No? It will form the image on the retina like this. This is the normal eye. But in the defective eye, the power of the eye lens is not enough to power of the eye lens. 25 here. Light rays are not exactly converge like this, no? The power of the eye lens is not enough to converge in the light rays. They are converging right here behind the eye lens. Then this eyeball is too short. This is the real eyeball. Here we have real eyeball like this. This is the real eyeball. This is the defective eyeball, defective one. Eye, here real eyeball. Done. That's it. Then, but right? This one shows the manageable position that the person can see. 25 centimeter won't be seen, but he can see at a point away from 25. Far away from 25 centimeter, he can see the object. This one is the objective distance. Here we have least distance of distinct vision. Exactly far away from the point of least distance of distinct vision. Now he can see. This is the clear appearance, shortest distance by the defective eye. This is called near point of the defective eye. Defective eye. Near point of the defective eye. Then this one is the corrected eye. Okay, then in the correction, you can remember like this. In the correction, these two light rays should be converged, which means converging property of this lens must be increased. Then you can manage it by reducing the refractive index in front of the eye material, which means, yeah, if the air density is reduced, which means if you can manage the vacuum in front of the eye, that may be corrected, right? The corresponding refractive index decreasement available in front of the eye, then these two light rays may be converged to the retina, right? Okay, it may be corrected, not exactly corrected, right? Okay, then here we have. Now, we can keep the object at the least distance of distinct vision. After keeping the object at least distance of distinct vision, this one is D. This should be exactly in front of the focus of this one, right? Then it forms an image. It forms an image right here. This one constructed one, then should be the broken line right here. And then here, light rays are converge right here. Done? Okay. What will happen here, Buddha? By keeping the object at least distance of distinct vision, D, this is the objective distance for the wearing lens. The worn lens is this one. This is the objective distance, here U. Then image will be formed near point of the defective eye. It serves as the object to the eye lens to form the image on the retina, same as this. Then after wearing the lens putti, after wearing the lens, we can rearrange the position of the object. It's a far position. 25 is right here, right? Without using the spectacles. Now, without using the spectacle, the least distance of distinct vision is 25 for the normal line. If you have eye defect, this should be the observing position that is called near point of the defective eye. You can't see here without using the spectacle. You can see here without using the spectacle. After the spectacles are worn, you can keep the object 25 centimeter. Then it serves as the object to the wearing lens and then will be formed the image at near point of the defective eye. It serves as the object to the eye lens, will form the image on the retina. That's it. Clear? Yeah. Then applying the lens formula for this one, will serve the objective distance here. Image distance is this one. For the focal length, this one. For the combination of these two, this should be the objective length. This is the image distance and focal length is the combined length, right? Okay, one by one, you can manage it, right? Okay. Then can we copy? First, second, third, and fourth, right? Right, Buddha. Can we write first point? In the long-sighted, 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 the close distance object can't be clearly seen. Long distance, long-sighted, close distance can't be seen. Next point. The diameter of the eyeball is too short. Diameter of the eyeball is too short than the real eyeball. Diameter of the eyeball is too short than the real eyeball. Than the real eyeball. Than the real eyeball. In this defect. Next point. But this person has the near point. This person has the near point. Near point, which is far away from, 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 least distance of distinct vision. Least distance of distinct vision. Least distance of distinct vision. After wearing the convex lens, 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 the object which is kept at, the object which is kept at least distance of distinct vision, least distance of distinct vision, is served as the object to, is served as the object to the wearing lens, wearing lens, and forming the image, and forming the image at the near point of distinct vision, at the near point of the distinct vision, at the near point of the distinct vision, near point of the distinct vision. Now it serves as the object to, now it serves as the object to, it serves as the object to, the eye lens, the eye lens, to form the image on the retina, to form the image on the retina, on the retina. Clear. Right, 286. A person of short-sightedness may be corrected when he is inside water pond. Explain this incident. Explain. Inside water, the refractive index of the outer medium, refractive index of the outer medium, refractive index of the outer medium, refractive index of the outer medium increases, then the ability of converging the light rays, then the ability of converging the light rays, decreases. That's enough, right? Okay. Next one, 287. A person of lone sightedness may be corrected when he is at the hillside area. Hillside, right, write down. At the hillside, density of air decreases. At the hillside, density of air decreases. At the hillside, density of air decreases. Density of air decreases. Then the ability of converging the light rays, increases. Ability of converging the light ray increases, right? Okay. That's enough. Next one. Explain how would the curvature of the eye lens is changed while looking the object at the different positions. Like this. When you keep the eye for the infinity long distance object, curvature becomes low, and it will be the natural condition of the curvature of the eye lens by forming the image on the retina like this. Infinity object. Curvature is very low. If the object is kept at least distance of distinct vision, D, to form the image on the retina, curvature should be large. Here, focal length is equal to the diameter of the eyeball. This is called maximum focal length. And here, focal length of the eye lens is like this position. By increasing the curvature, radius of curvature decreases by reducing the focal length. This is called minimum focal length. minimum focal length here. This one is the object. And here we have focal length. Clear with that? Right. Okay, then you have to say, when the person looking at infinity object, focal length is large and curvature should be low. Write down that one. Observing infinity, curvature, observing infinity, curvature, curvature is low, focal length is large. Next line. Observing least distance of distinct vision. Observing least distance of distinct vision. Least distance of distinct vision. Curvature is high by reducing the focal length. By reducing the focal length. By reducing the focal length.